So we are in chapter 9 of your chemistry book, and we're coming to the end of section 1, which is quite a long section. And then we're going to go over the chapter review and also your quiz. I think it's quiz 14. So what we've been talking about is the types of chemical bonds. And so we talked about the ionic bond, the covalent bond, and the metallic bond. The ionic bond is basically when ions transfer electrons to another one, and then they become two ions, one's positive and one's negative, and that holds them together. And that's what happens in stable or table salt. So, and then on to covalent is sharing. Co means share, valent, they're sharing valent electrons. So they're the sharing of electrons. It all has to do about electrons. And these covalents are usually nonmetals of similar electronegativity. That means basically electronegativity means how they attract electrons. So basically that's sharing. Metallic is going to be that delocalized electron cloud around metal atoms that actually many atoms share all the electrons. As electrons flow freely, delocalized means they're not in one locality. They're delocalized electrons flowing through, and those are the atoms that are metals. Like, you know, if they're just a metal like zinc, copper, any kind, or even two metals, they're going to be all metallic. So let's look at this bond here. We see the main ionic bonds being over on this side. You have, sodium chloride and magnesium chloride and aluminum chloride right here, all important. And onto it, and you'll see. But as they get down into just the metals and just metals, they're going to be all metallic. And then the covalent's going to be over on the right side. Basically, we'll have a lot, well, I say right side, not totally on the right side, but there'll be things like, covalent, as for like phosphorus chloride and such. It's when you have two non-metals coming together, you have these covalent bonds. So this tells we have ionic, we have covalent, and we have metallic. So, but there's going to be another bond that we're going to talk about here. So, it says it's tempting to think only in terms of ionic, covalent, or metallic bonding, as if there were distances delineated, but some categories, and in most cases, they have bonding in chemicals that are not completely ionic and not completely covalent and not completely metallic. So they kind of mix there. It's just saying you can't say 100% that they are that way in the midst of all of their combinations. So a guideline is a bond is considered predominantly ionic if the electronegativity difference, En, that's the En, of the two bonded atoms is greater than 1.7. So if you take the two atoms that are bonding together and you subtract that difference, if it's greater than 1.7, it's going to be ionic. So, and there's a table on page 126 that talks about this. And the table in 9 right here, this one shows the percentages here, shows the relationship between the electronegativity difference and the percent ionic or covalent character. Of course, if it's great electronegativity, that means they really draw each other together, such in that electrode, it's going to be, the percent is going to be ionic, okay? So here you have, if they have a electronegativity of 0, they're 100% covalent. All the way up to 1.7, they're going to be 40% ionic, and then only 60%. So it's kind of weird, but they tell you what percentage. They go all the way. Say that the number is 3. If it's a big number, it's going to be 90%. Anything above 1.7 over here is going to be predominantly ionic, because ionic means when they have a big number, that means they really attract electrons together, so they're going to be very ionic. So the number above 1.7 is going to be 90% ionic. And there's another chart. Let's see, I don't want to go back to that chart right now, but it's on page 126 that talks about this electromagnetic. Maybe I should try to go back to page 126 and show you. Let's go back here. Hopefully my computer is working okay. Oh, what did I say? 126. We're on 125. Here we go. This table here. This tells, you know, you can see where the blue is all metals. And of course, these are non-metals and these are semi-conductors or semi-metals. And here we have, but the inner transition, you have all these numbers. So this tells the number, and then you subtract this number by this number. And if you, whatever you get, say you had, say you were doing, let's see, sodium and fluoride here, and they were combining. So you'd say it'd be very ionic because you take 4 minus 9 and you're going to get 3 something, so that's going to be a high number, so that'll be ionic. Notice that these ionic numbers have very high numbers on this side compared, you know, 4, 3, 2, all of these are pretty high, all above 1.7. And then the metals here all having, you know, although some of them having higher numbers down here. But when you find the difference and the difference is above 1.7, it's probably going to be ionic. So just subtracting one of them from the other one, you could, as they're combining together, you can find out what the combining power is, you know, so. Let's go back, see if I can go back to the same place. Okay, here's where we were, good. So let's go on to another, example 9.2. That's because you're gonna have some of these on your test questions too. Not much, but anyway, predict what type of bonding predominates in each of the following. So first of all, you look at Ag. What's Ag anyway? You guys remember? Silver, right? That's the number for silver. Silver is a metal, so it's going to have metallic bonding. We know that. So now we have hydrogen and oxygen, H2O. What's that? Water. It's composed of 2 nonmetals, and so you're going to have covalent because they're 2 nonmetals. So this one is magnesium chloride. It has a metal and a nonmetal. So this is more complicated to find out exactly what it's doing. But you see down here is a compound of a metal and a nonmetal. Ionic bonding is predicted because you subtract the magnesium from the chloride, which you get 3 minus 1.2, and you'll get 1.8. 1.8 is above 1.7. So some of it's going to be predominantly ionic. Ionic's going to predominate it, but it could be, plus there could be a lot of covalent there. That's the kind you have to be more careful up there. So now we have FeMg, this one here. What was it? FeMg, you want to know what that one is? Iron, Fe means iron, and magnesium, they're 2 metals, right? So if they're 2 metals, they're going to be, going together, they're going to be metallic, you know, so 2 metals are always, so. And then on to silicon and chlorine. So it's a combination of silicon's a semi-metal and a non-metal. So what's a semi-metal? In bonding, semi-metals behave more like non-metals. So basically we don't have a metal. So then we take on that chart that I had, and you take silicon, which is 3 minus 1.8, you're going to get 1.2. So this is a low number, lower than 1.7. So the bonding is going to be predominantly covalent. So you can use that chart. I don't have to memorize those numbers. At least that would be hard if you had to, because there's so many of them. So now we're going to talk about something new, but it has to do with bonds. Not only do we have the bondings of ions and covalent and metal, now we have another thing that we have to be concerned about, because this actually holds things together too, and gives them charges. As you say, unlike charges come together and hold together, right? So we're going to talk about polar bonds, and this is going to be unequal sharing, called unequal sharing. You have 2 bonds that have two different as for electro, like either negative or positive, what you call it, electron negativity. You have 2 different, and then what happens, you'll have a polar bond. So first of all, Non-polar, what's non-polar? Covalent bonds are where two electrons are shared equally. And so they have really no poles because they're all equal, right? So they might have two different atoms, but neither one of them has a positive and negative pole. Those are called non-polars, but they have to be equal in symmetry to be non-polar. And then you have the polar type bond. The polar type bond is going to be that bond if one atom has more electronegative than the other. On the other side, you're going to have a stronger pull. So this one-sided pull is going to cause electrons to be unequally shared. Because we have electron cloud there, you see that electron cloud, it's going to be distorted, and because they're unequal. And the greater the difference of being more distorted, then one side is going to gain a partial negative charge, and the other side is going to have more of a positive side, so you're going to have a higher concentrations of negative on one side. So if you look right here, we have a non-polar bond. These are basically, these two atoms are exactly alike, and they're bonded together, and they're very symmetrical, so they don't have any electric poles because they're just equal. So now you have two atoms here, and you have one who has, and see this little sign here? It looks like an S with a bottom of an 8. It looks like the top is an S and the bottom is an 8. That means partial electric charge. So this side's going to be partially electric negative because look at all the electrons it has over on this side, and this side is going to be partially positive. But you see how these two atoms are not equal. So they're going to have, one's going to have a polar side that's good, the North Pole or whatever. The North Pole is going to be real negative, and the South Pole is going to be real positive. So they kind of pull in that way. And this way, they will be drawn to other atoms that have the same charge, and this will hold a lot of different things together, especially water, because water is very, very polar bond with hydrogen and oxygen. So let's talk about this here a little more. See if I covered it. I got those partial charges right down here. It says a partial charge is only a fraction of the full charge, as +1 or -1. But partial charges are used by this little. It's actually a lowercase Greek delta, and it looks like it's a S on the top and an 8 on the bottom. So it almost looks like an 8 with a missing piece in there. But that is what we call a partial charge. So an example of a partial charge here would be hydrogen and chlorine. And you see hydrogen, because it will have a more positive charge as the chlorine atoms are bigger, drawing it in there. So you'll end up having a polar. You'll have one having a positive pole and one having a negative pole. That's polar. One has a positive pole, one has a negative. Similarly, a molecule of carbon monoxide, here we have carbon and we have oxygen, and you have a triple bond there. They're sharing 3 electrons. Actually, there'll be 6 because it'll be 3 of each. Or, so you have, 6, 7, 8, 6, 7, 8. But they'll be changing. But one side, it's going to be very polar because you'll have in the midst of this, you'll have a positive pole and a negative pole. That's what polar means, a positive pole and a negative pole. And it's an unequal bond, right? And how they represent this here, as you see, they call a bond or molecule that has a negative end and a positive end. A polar bond or polar molecule forms what's called a dipole. Because it has 2 poles, it's called di. Di means 2 poles. And both carbon monoxide and hydrogen chloride, those 2 are dipoles, as you see in this picture. HC, HC. And see how they wrote where the charges are going. So this arrow that they put in here, the polarity of a bond or molecule can be indicated by an arrow pointing toward the more negative end. It always points to the more negative, or the end that has the most electrons. So that's how they did that. So if you see those arrows, it's pointing to the one that's more negative or has the most electrons. Okay, now we're going to go over what's going to be on your section review, just so you know some of these things. And I will, we'll go over these first ones, and then I'll go over the application really quick. And then we'll go over your test if I have time on here. So, concept review. Give 3 properties of ionic compounds and 3 properties of molecular compounds. What did we say? Let's see if you can see maybe you can see right here. Okay, properties here. Ionic compounds, they have crystal-like, and they have high melting point. They're soluble in water, and they're good conductors. And on to the compounds. Regular compounds are opposite. They have a lower melting point. They're gas, liquid, and solid. So they're a little different. It's for the compounds. So those 3 characteristics to give. The next talks about the octet rule. What do you think the octet rule is? The octet rule being being what? 8. Atoms react to achieve a noble gas state. What's a noble gas state? 8. They want to be 8s. So, as you say, I don't want to be late, I want to be an 8. Octet meaning 8. So, to fill up their whole electron shell, you have to have 8, and that's what noble gas. So they want to be like a noble gas and fill it up. Why might this principle be considered the driving force that causes elements to react to form chemical bonds? Because basically atoms wouldn't be seeking anything. They'd be alone, wouldn't they? They need to seek something so they can combine and form new substances, or else all we would have is the elemental chart and no other substances if that didn't happen. So define ionic bond. Let's see if I can put this under here. Ionic bond is the transfer of electrons one atom to another. You see that there? And then on to define covalent bond. Covalent bond is the sharing of electrons. To have a mutual attraction to each other, they share. Co means share, actually. Cooperate means sharing. So covalent means your valence. So you're sharing valence electrons. So the next one says, give 2 examples of covalent networks. We have 2 examples, and you look in your book there. Diamonds. What is a covalent network? A covalent network is when you have a lot of atoms sharing with each other, and they're sharing with one, sharing with another, so you have a hope. Especially this happens really a lot in carbon, and so when we have carbon, because carbon has 4 different electrons to share, the carbons come together, and as these carbons come together, you'll have these networks. And diamonds, of course, is a carbon covalent network. And we saw examples of that in your book here. So what is a metallic bond? Well, a metallic bond, basically, here's the definition. Metallic bond, let's see, number 6 there. Metallic bond is sharing a sea of delocalized electrons. So you have these electrons which are delocalized. That means they're free. And they're flowing through in the midst, and all of the different atoms are sharing this, and it's always with metals. It happens with metals, and that's how come metals conduct electricity really well. So let's go on to write the Lewis structures of calcium and fluorine atoms. If calcium and fluorine atoms are allowed to react, what would be the Lewis structures of the resulting ions? So the Lewis structures, you have to write them, so I'm going to show you how I did it. Okay, see if you got here. So we have the Lewis structure here, the applicated Lewis structure. We have calcium has 2, and the fluoride. Okay, the fluoride actually, if you looked at it before, the fluoride would have 1, 2, 3, 4, 5, 6, 7. See, there's a 7. So these haven't combined yet. So this one has 7. It needs 1 more there, doesn't it? Calcium has 2, so you're going to need 2 fluorides. Because calcium is going to want to put one of its ones in here, and this fluoride, he needs 2 of these because they have 2 of them to get rid of. So this is what it's going to look like. You're going to have fluorine on this side, and you're going to have another fluorine on this side. There's the calcium, and it has its 2, and it's going to share those 2 with 2 different fluoride guys. So now you have fluoride, calcium, and fluoride. That's how it's going to look. It's going to look like that. So all the F's going to have, here, the fluorine's going to have 8. This fluorine's going to have 8. And the calcium has 2 to share, right? So this is what it looks like. And those are the Lewis structures. Lewis structures are really handy. So let's see. We did that. Okay, number 2. Which of the following compounds would you expect to contain ionic bonds? And which one would you expect, and which of these compounds would you expect to have the most ionic character? Well, you can take each one of these and subtract them in that table that we had, remember? And you can find out, subtract this by that, and if it's above 1.7, it'd be ionic. But you can kind of look here, as you can look, and if you look and see where these are on the table. So let's go back to that table and I'll show you. It's always good to have a periodic table in front of you. Okay. I think I'm too far here. Here we go. Right, here's our periodic table. Let's go back to page 115. So now you can see here. So if I say, here's my what I'm looking for. I'm looking for, see, predicting here. Let's see, number 2, SRI, SO2, lithium, oxygen, bromine, all of these, and we want to know which ones are. And when we look on these, let's look at where they're on the table. The first one we have is SR and I. So if we look, basically looking for SR, it's clear over on this side, and I is clear over this side. Very ionic because they're in the opposite. And the next one is SO2. So you're going to have sulfur, and you're going to have oxygen here. So what does that look like? There's no metals there, and they're right here, sulfur and oxygen. So it looks very much they're going to share each other, covalent, because they're not on both sides. The next is lithium and oxygen. Where's lithium? Way over on this side, and oxygen's way over on this side, so they're going to be very ionic. Remember, they're ionic if they're way apart, because they have a high electromagnetic attraction to each other. And then you're going to have bromine, let's see, bromine and chloride. So, I don't know, bromine and chloride. Okay, they're another one. What would you say that one? I would say that one would be bromine and chloride right here, because they're right next to they're right under each other. They're not across. They'd be very much covalent. So that would be a covalent one. So the ionic one so far would be, basically, well, I'll go back to that and show you which ones. Basically, you'll see which ones. But when you go back and forth, so let's go on to CS and FS. CS is way over in this. It's going to be very much ionic, right? CS and fluoride. One's way at this point and one's way at this point. So they're going to be the most. CS, he's way over on this, way over in this. But they're going to be the most negative. So they're going to be very ionic, the most ionic. And then we have calcium and chloride. Calcium's on this side and chloride's on this side, another ionic. So you get the meaning of all that, okay? Let's go back to our questions. Okay. Okay, so that's this. So you would say, we went over those. Which ones were ionic? As we saw this one was ionic, this one was ionic, this one was ionic, and this one was ionic. But the most ionic would be the CS and F, because one was in the way over in the left and on the bottom, and one was way over in the right. So this would be the most ionic character, this one. Which one do you expect to have the most? That one. So now we're going to draw these Lewis structures for each of the following. So what following do we have? An iodine atom, an iodine molecule, and an HI, hydrogen iodine molecule. So I did these. These are not very hard at all. And these are kind of fun to do too. Let's see if I can get them plugged in here. So here is just an iodine molecule. It has 1, 2, 3, 4, 5, 6, 7. It's a halogen, so it's going to have 7. It needs one more right here at the top to be full. That's the one it's interested in. So that's the molecule. Now we have two of these two molecules want to stick together. So we have two of them. 1, 2, 3, 4, 5, 6, 7. And then you 1, 2, 3, 4, 5, 6, 7. So you have 7 here, but you're gonna want 1 to share here. It looks like I had 2 to share, but I don't know why I put that 1. But there's one of them here that they're gonna share, and because they're sharing, they're gonna be hooked together about that one that they're sharing. So, and then hydrogen iodine. Here's hydrogen, and here's iodine. Has 1, 2, 3, 4, 5, 6, 7. It needs 8, so it's gonna want to take that. So it took the hydrogen and made an ion. And that's what happened right there. So, okay, let's go over now the next here where it says, predict what type of bonding predominates in each of the following. So how would we see if it's covalent or ionic? Well, one thing you can do is go to that chart and subtract AS from Cl, and if it's more than 1.7, it's going to be ionic. That means it's very, very electronegative, which means it really wants to attract electrons. So, but you could also kind of look and see if they're metals or non-metals. So what I did again was look at these where they were at. So let's go back to that table. Always go back to your periodic table, because then you're going to need that all the time. Here's the periodic table again. So to do this here, we're going to, the first one was arsenic and chloride, AsCl3. And so we're going to look at where these are on here and see what if they're covalent or not. So here's arsenic right here on this side. It's a semi-metals, but semi-metals act like non-metals. So, and then you're going to have Cl. So if you have 2 non-metals, then this is going to have to be covalent. They're both over on this side, right? So the next one is lithium and bromide. So we have lithium right here, very, very strong alkali metal, and it's going to be combined with bromine. So where is bromine? Right over here. Of course, this is way over here, and this is way over here. You have ionic. The next one is copper and nickel. So let's see, here's nickel, here's copper, they're right here, they're 2 metals. If they're 2 metals, they're gonna be metallic, right? So they're gonna for sure be metallic. And so here we have sulfur, which is S right here, and oxygen. They're gonna be very much covalent, huh? Sulfur and oxygen, because they're both non-metals. And then we have xenon, which is right here. It's actually a noble gas, so it really doesn't want to combine, so it's not going to be covalent. And you have xenon with F here, so basically they're both non. So I just put with both of those two that these two together would probably have to be covalent. I don't know how, but this one's being a noble probably wouldn't combine well with that. So noble gas. I don't even know why they put that one in there. But the next would be iron and let's see, just iron. Iron is Fe. So let's see, where's well, it's just iron. Fe is just iron. Iron is all totally metal, so it would be a metal, that's for sure. So why don't I know where? All right, I don't know. Well, there it is right in front of me. I should have known that one right there, iron, very common one. So iron there, and zinc up here. All these metals, if they're just metals, they're just gonna be metals. And so then we have MnF2, and with that one, I went ahead and tried to figure that one out with the Mn, and I put down, let's see, let me put down, MMF2, I put ionic because when you take it on that chart and you take the electronegativity of one minus the other, it was above 1.7, so mostly ionic. The next one is HCN. I put covalent because each one of these have to hook onto the other. There's one, two, three molecules. 3 molecules can't totally be ionic, you know, so that's what I thought. That one might be kind of a questionable. And then you have onto aluminum and oxygen, which you're going to have be ionic. Basically, aluminum being a metal and oxygen being a non-metal. And if you add those up, it's going to be ionic. We had that on the chart, Potassium and chloride, of course, is going to be ionic. Potassium's clear over here, chloride's over here, ionic. And then we have Cr, which is a lone metal. That's going to be metal, of course. So let's go back and let's finish up real quick. I'm right at the end of here, and then I'll do the quiz in the next one, I guess. This last bit here says, so we did this one. Tell whether the bonds between the following atoms are polar or non-polar. So these are looking at these bonds. We're going to look and see, and if they're equal or non-equal. Remember, if they're not equal, they're not going to be. So if you look at Si and Si, you know that one there is going to be non-polar, because if they're non-polar, they're the same, they're equal, they're not going to have positive and negative poles. So that one, and oxygen there's another one there, and chlorine here, those that have the same, they're going to be definitely equal, so they're going to be non-polar. So, and then as for hydrogen and oxygen, that is a very, very polar one. You know, that's going to have a negative and positive. And then carbon and hydrogen, I would say that be non-polar, just because when you put it together, hydrogen's going to be 4 so hydrogen on this side, hydrogen on this side, hydrogen on this side, hydrogen on this side. So I'd say that this is going to be non-polar. I'm not sure. This is the one I'm not so sure about. Carbon and oxide we know is non-polar. This one, non-polar, because it's very equal on each side. Very close. If you take them and subtract them, very close. Mainly, I'd say mainly non-polar. And then Cl and F, I would say would be very non-polar, because Cl and F are both halogens. They're hooking onto each other. So this one would be non-polar. This one here, N, is very polar. Nitrogen and hydrogen, very polar. One positive and the other one, because they're very much unequal. So you just have to find if they're symmetrical or not to find out whether they aren't. So I'm going to stop there. And hopefully we're going to go on to section 9 too, but I'm going to do a quiz and a little video with a quiz on it. So.